You have never seen the largest waterfall on Earth. Nobody has. Not because it's in some remote jungle or behind a restricted border, but because it's sitting at the bottom of the ocean, under 3,000 meters of water, and it has been falling continuously for millions of years while the surface world stayed completely unaware. Angel Falls in Venezuela is what most people think of when you say, world's tallest waterfall. Nearly a kilometer of free fall off a sandstone cliff, it's genuinely spectacular. Compared to the waterfall we're talking about today, it looks like a tap left running. The underwater waterfall at the Denmark Strait drops over 3.5 kilometers, nearly 4 times the height of Angel Falls, and the volume of water moving through it every second is 5 million cubic meters. To put that in terms that actually land, the Amazon River, the biggest river on Earth by flow, moves around 200,000 cubic meters per second. This waterfall moves more than 20 Amazons simultaneously, every second, without stopping, in a place no human eye has ever directly seen. Right now, while you're watching this, it's running. Most people go their entire lives without hearing about this. Geography classes skip it. Nature documentaries gloss over it. The reason is almost funny. It's invisible. Standing on a ship directly above it, you'd feel nothing, hear nothing, see nothing but flat, cold ocean water. 3.5 kilometers beneath your feet, the largest waterfall on the planet is in full force, and the surface gives absolutely no indication of that. That's what this video is about. And once you understand how it works, the ocean is never going to look the same to you again. The Denmark Strait is the gap of water between Greenland and Iceland, about 800 kilometers wide, cold, regularly crossed by shipping and fishing vessels. Nothing about it looks unusual from above. Everything about it is extraordinary from below. Understanding the waterfall means understanding one simple fact about water. Cold water is heavier than warm water. Dense water sinks through lighter water, exactly the way a stone sinks through air. In the ocean, density is controlled by 2 things: temperature and saltiness. The colder and saltier the water, the denser it is, and the harder it wants to fall. On the Arctic side of the Denmark Strait, the water spends winter being cooled by Arctic air to near freezing temperatures. When seawater freezes at the surface, the ice that forms is nearly pure water. It doesn't carry the salt with it. That salt gets expelled into the water just below, making the water under Arctic sea ice simultaneously ice cold and extra salty. Cold plus salty equals extremely dense. Extremely dense means it's looking for somewhere to go down. On the Atlantic side, coming up from the south, the water is warmer and fresher, lighter. When these 2 water masses meet at the underwater ridge running between Greenland and Iceland, the Arctic water reaches the edge of that ridge and does exactly what any heavy fluid does when it reaches a drop-off. It falls down the underwater slope, accelerating, pulling more water in behind it, growing. The Denmark Strait Cataract, which is what scientists formally call it, has been doing this for roughly 3.5 million years, continuously, through ice ages and warm periods and everything in between, with no pause and no sign of slowing. How scientists even figured this out is a story worth telling, because nobody went down to look. Getting to those depths in a vehicle that can make meaningful observations requires specialist research submersibles, and even those don't operate comfortably at the base of the Denmark Strait. The discovery came the slow way, through temperature measurements taken at various depths across the North Atlantic over many decades. What oceanographers kept finding was that certain deep regions of the Atlantic were filled with water that was extraordinarily cold. Colder than the water around it. Colder than the slow drift of ambient deep ocean water could explain. Something was delivering cold water to those depths at a rate that overwhelmed the local temperature. And when researchers worked backwards through the math, the source kept pointing north, toward the Denmark Strait. Current meters were eventually deployed, instruments lowered to depth on cables that measure how fast water is moving and in which direction. The readings from the Denmark Strait were, by deep ocean standards, startling. The flow down the underwater slope was moving at speeds that made it one of the fastest sustained currents in the deep ocean anywhere on Earth. Multiply that speed by the cross-sectional area of the flow, and you get the volume. 5 million cubic meters per second. More than 20 Amazons. That's when people started paying real attention. The 5 million cubic meters per second figure matters, but the way the waterfall actually behaves is even more interesting than the number suggests. As the dense Arctic water tumbles down the underwater slope, it creates turbulence around it. That turbulence pulls in surrounding water, drags it along, mixes it in. The technical term for this is entrainment, and what it means in practice is that the waterfall amplifies itself as it descends. By the time the descending mass of water reaches the floor of the deep Atlantic, it's carrying roughly 10 times the volume of water that originally started the fall at the top of the slope. 10 times. The waterfall essentially generates its own supply chain as it goes, recruiting water from its surroundings and adding it to the flow. What begins as 5 million cubic meters per second becomes something closer to 50 million by the time it spreads out across the Atlantic floor. That water then fans out across the deep basin. It doesn't hit a pool at the bottom and stop. It spreads laterally, carrying its cold, dense characteristics across thousands of kilometers of ocean floor. Over decades and centuries, this water from the Denmark Strait slowly fills the deep North Atlantic, maintaining the temperature and chemistry of that entire layer of the ocean. Stop the waterfall, and the deep North Atlantic starts to change. It's that fundamental. Here's where it gets personal in a way that's easy to miss. Water formed at the surface of the Greenland Sea last winter. Water that was sitting in contact with Arctic air, getting cold and salty, is making that descent right now. In the span of days, it will go from being surface water exposed to open sky to being deep Atlantic water 3.5 kilometers below the surface, beginning a journey along the ocean floor that will take centuries to complete. Some of the water currently sitting in the deep North Atlantic made that same descent during the time of the Renaissance. Water that was at the surface of the Greenland Sea while Michelangelo was painting the Sistine Chapel has been drifting slowly along the ocean floor ever since, and it hasn't come back up yet. The deep ocean doesn't move fast, but it moves constantly, and it moves because of a waterfall that nobody can see. What's strange and genuinely hard to sit with is that this isn't rare or exceptional. The Denmark Strait Cataract isn't some geological freak. It's one of several major underwater waterfalls operating simultaneously around the world, all doing versions of the same thing, sinking cold, dense water to depth and feeding the ocean's deep circulation. The Denmark Strait just happens to be the biggest one, by a lot. The second largest is the Faroe Bank Channel overflow, just southeast of Iceland, another location where cold Nordic seawater pours over an underwater ridge into the deep North Atlantic. Smaller than the Denmark Strait, but still enormous by any surface world measure, and operating on the same basic mechanism. Down near Antarctica, a related but even more dramatic version unfolds at continental scale. In winter, when Antarctic temperatures drop and sea ice forms around the entire continent, cold and salty water accumulates along the continental shelf. That water is among the densest anywhere in the ocean, cold from the polar air and salty from ice formation. And when enough of it builds up, it spills off the shelf edge and cascades down the Antarctic underwater slope. The result is Antarctic bottom water, the densest, coldest, heaviest water in the open ocean, spreading from Antarctica across the floor of every ocean basin on the planet. Finding Antarctic bottom water in the deep North Pacific isn't surprising to oceanographers. It's expected. That water traveled from the coast of Antarctica, along the ocean floor, through the Southern Ocean, and into the Pacific Basin. A journey measured in thousands of kilometers and hundreds of years. The fact that it's identifiable at that distance by its distinct temperature and chemistry tells you how coherent these underwater flows are. They don't blur out immediately. They hold together, maintaining their character, spreading their influence across the full depth of every ocean on Earth. For most of human history, none of this was suspected. The deep ocean was assumed to be still, not just calm, but genuinely motionless. A static abyss sitting untouched below the active surface. This made intuitive sense, given that there was no way to measure it. Surface currents were obvious. You could see them, feel them in a ship's drift. Deep currents were invisible, and invisible meant absent to anyone without the instruments to detect them. The first real cracks in this assumption came from temperature measurements in the mid-19th century. A British naval officer named James Clark Ross, on Antarctic expeditions, lowered thermometers into the deep ocean and found bottom water temperatures so cold that they couldn't be explained by surface water slowly cooling as it sank. Something was delivering very cold water to depth actively, not passively. That observation sat without a good explanation for nearly a century, until better instruments and more systematic measurement campaigns began building the picture of what was actually happening down there. Thermohaline circulation became the name for the whole system. Circulation driven by heat and salt, rather than by wind. Scientists began mapping it using temperature and salinity measurements at thousands of points across every ocean, cross-referencing the data, tracing water masses by their chemical fingerprints. What emerged was a planetary circulation system of extraordinary complexity and scale, with the underwater waterfalls at its downward heart. The conveyor belt analogy came later, and it's imperfect but useful. Warm surface water flows north in the Atlantic, cools, becomes dense, sinks via the waterfalls, flows south along the deep floor, eventually circulates into the Pacific and Indian Oceans, slowly rises back toward the surface over centuries, warms up, and returns north. The loop takes somewhere between 500 and 1,000 years to complete, and it moves heat around the planet in amounts that shape the climate of every continent. That connection between an invisible underwater waterfall and the climate of the surface world is the thread that runs through the rest of this video. And it starts with the fact that the conveyor belt needs the waterfalls to run. Stop the sinking, and you stop the circulation. Stop the circulation, and the heat stops moving. What that actually looks like, and what it has looked like before, is a story that makes the waterfall feel considerably more urgent than a geographical curiosity. But that's part 3. For now, let the water fall. Somewhere in the North Atlantic right now, in complete darkness, in water a few degrees above freezing, the Denmark Strait Cataract is moving at full pace. 5 million cubic meters per second, cascading down a 3.5-kilometer underwater slope, entraining 50 million by the time it reaches the floor. Nobody is watching it. No instrument currently deployed is imaging it in real time. We know it's happening from measurements and models, and the unmistakable signature it leaves in the deep Atlantic's temperature and chemistry. That's enough. We don't need to see it to know it's real. The ocean has been running this system far longer than we've been around to ask questions about it. And it will keep running long after the last measurement buoy rusts off its mooring cable. The waterfall doesn't need us to understand it in order to work. There are lakes at the bottom of the ocean. Not loosely defined zones of water with slightly different properties. Actual discrete bodies of liquid sitting in basins on the seafloor, with a surface you could pour a boat onto. Except nothing about this lake behaves like a normal lake, because what fills it is far denser than regular seawater. The danger is not depth, but chemistry. An oxygen-starved, hyper-salty body of brine that most animals cannot survive once they cross the surface. These are called brine pools, and the physics that creates them is the same physics running the Denmark Strait Cataract, just in a completely different setting. At certain locations around the world, particularly in the Gulf of Mexico and the Eastern Mediterranean, ancient salt deposits are buried under the ocean floor. These formed millions of years ago when sections of ocean basin dried up, and the evaporating water left behind enormous quantities of solid salt. Over time, new sediment piled on top, burying everything. But the ocean floor isn't sealed, and seawater slowly percolating through the sediment reaches those salt deposits and begins dissolving them, becoming a brine so concentrated that its salinity is several times that of normal seawater. That super dense brine migrates upward, seeps out onto the ocean floor, and because it's far too heavy to mix with the water above it, it pools in hollows in the seafloor. What you get is a standing body of fluid on the ocean floor, with a sharp, clearly defined surface, a shoreline where the brine meets the regular seawater above. Small waves form at that interface. The boundary is as distinct as any surface lake's edge. Submersibles that have descended to these brine pools and filmed them have captured something that looks genuinely wrong. An underwater shoreline at the bottom of the Gulf of Mexico, with actual wave action at the interface, sitting under a kilometer or more of ocean. A lake inside a sea. The same principle. Denser fluid pools beneath lighter fluid, just expressed at a completely different scale and in a completely different location than the Denmark Strait. The brine itself is almost entirely lethal to any animal that enters it. It's anoxic, nearly devoid of oxygen, and the concentration of dissolved minerals disrupts cellular chemistry rapidly. Animals that wander too close to the shoreline and cross into the brine are overwhelmed quickly, which is why the edges of brine pools are often marked by rings of dead crustaceans and fish, casualties of a boundary they couldn't detect until it was too late. Around the margins of these pools, though, life concentrates in ways that are hard to square with how hostile the environment looks. Mussels cluster in dense beds along the shoreline. Tube worms anchor into the chemically rich sediment at the edges. Shrimp gather where two very different chemical environments meet. None of these animals are photosynthesizing. There's no light here. What they're running on is the chemistry the brine releases. Methane and hydrogen sulfides seeping up from the ancient salt deposits. Chemicals that specialist microbes can harvest for energy the way plants harvest sunlight. The microbes form the base of the food web, and everything else eats them, or eats what eats them. A toxic lake that supports a thriving ecosystem at its edges, on the floor of the Gulf of Mexico, powered by geology that is millions of years old. And it has its own waterfall. Where the brine pool fills past the rim of its basin and overflows, the brine cascades down the outer walls of the hollow. A brine waterfall. Dense fluid falling through surrounding seawater, driven by gravity, confined by terrain. Smaller than the Denmark Strait by orders of magnitude, but mechanically identical. Dense fluid falls. It's the same sentence at every scale. Rivers come next, and this is the one that genuinely surprises people. Off the coast of Turkey, where the Black Sea connects to the Mediterranean through the Bosphorus Strait, researchers lowered instruments into the deep channel in 2010 and found something they measured twice before they were comfortable reporting. The Black Sea receives fresh water from the Danube and other major rivers, making it significantly less salty and therefore lighter than the Mediterranean. When those two bodies of water meet at the floor of the Bosphorus, the heavy Mediterranean water doesn't mix evenly with the lighter Black Sea water. Instead, it flows as a coherent, channeled current along the seafloor, moving toward the Black Sea at depth, while lighter water flows the opposite direction at the surface. What the instruments found in that bottom current was a proper river, not a diffuse flow, but a channeled stream cutting through the sediment, with meanders, with banks, with deeper pools at bends where the current slowed, with sediment deposited on the inside of curves and eroded from the outside. Every structural feature that characterizes a surface river was present, just entirely submerged in the floor of the Bosphorus, invisible from above, running steadily in the dark. At full flow, that underwater river was moving more water than the Rhine. Researchers had been taking boats through the Bosphorus for decades without knowing there was a river flowing in the opposite direction directly beneath them. The Mediterranean adds another layer to this through Gibraltar. Heavy evaporation in the Mediterranean, driven by the intense sun and limited rainfall across the basin, makes Mediterranean water saltier than Atlantic water. That dense, salty Mediterranean water sinks, collects in the deeper parts of the basin, and when it reaches the Strait of Gibraltar, it doesn't flow out on the surface. It flows out underneath, a dense underwater current pouring through the deep section of the strait into the Atlantic. At the Gibraltar sill, where the seafloor rises before the Atlantic, the dense Mediterranean water reaches a drop and cascades over it into the deeper Atlantic basin. Another underwater waterfall, smaller than the Denmark Strait, but operating continuously for at least 5 million years since the Atlantic and Mediterranean were reconnected in their current configuration. The Mediterranean has been quietly contributing its excess salt to the Atlantic through a hidden waterfall for longer than our species has existed. That Mediterranean outflow water doesn't reach the Atlantic floor. It's dense, but not as dense as the coldest polar bottom water, so it settles at an intermediate depth, several hundred to 1,000 meters below the surface, and spreads westward as a distinct water mass. Oceanographers can trace it thousands of kilometers from Gibraltar by its salinity fingerprint. Every cubic meter of mid-depth Atlantic water at a certain latitude carries some contribution from the Mediterranean, delivered there via an overflow that nobody on the surface has ever seen. When you add all of these together, the Denmark Strait, the Faroe Bank Channel, the Antarctic Bottom Water Formation, the Gibraltar Overflow, the brine rivers of the Gulf of Mexico, the channeled flows of the Bosphorus, a pattern becomes clear that changes how the deep ocean looks as a concept. The deep seafloor is not still. It's shaped, scoured, channeled, and fed by a continuous network of dense fluid flows running along its surface, invisible from above, driven entirely by density, sculpting the landscape of the ocean floor the same way surface rivers sculpt the landscape of continents. Channels carved by the southward flow of North Atlantic deep water stretch for hundreds of kilometers along the Atlantic floor. Fields of sediment ripples mark the paths of bottom currents, the way sandbars mark the beds of surface rivers. Where these flows bring oxygenated water from the surface, life concentrates on the otherwise food-sparse deep floor. Where the flows are weak or absent, the deep basin grows oxygen-poor and nearly lifeless. The geography of deep-sea biology is essentially a map of where the underwater waterfalls deliver their water, and how recently. That delivery system is also the planet's main mechanism for moving carbon from the surface into long-term storage. Surface water absorbs carbon dioxide from the atmosphere as part of normal chemistry. When that water becomes dense enough to sink, through the same cold, salty process driving the Denmark Strait, it carries its dissolved carbon load to the deep ocean, where it stays out of the active atmosphere for the duration of the deep circulation cycle, hundreds of years in most cases. The ocean currently absorbs around a quarter of all the carbon dioxide humanity produces. A substantial portion of that absorption eventually gets transported to depth via these same sinking currents. The underwater waterfalls are, among their other roles, part of how the planet manages the carbon balance of its atmosphere. That connection becomes the central thread of Part 3. For now, the deep ocean is not a quiet, motionless abyss. It's one of the most dynamic systems on Earth, just operating at scales of depth, darkness, and slowness that make it invisible to everything living on the surface above it. There's a conveyor belt running through the ocean, and it's been running for millions of years. Not a physical belt, but a system of currents so consistent and directional that the conveyor belt image is what oceanographers themselves reach for when they want to explain it quickly. Warm surface water flows north through the Atlantic, carrying heat from the tropics toward Europe and the North Atlantic. As that water moves north and cools, it becomes dense enough to sink, feeding the underwater waterfalls described in Part 1. That sinking water then flows south along the deep ocean floor, circulates through the Southern Ocean, and eventually makes its way back toward the surface over centuries. Then it warms, flows north again, sinks again. The loop takes somewhere between 500 and 1,000 years to complete, moving that volume of water and the heat it carries over that kind of distance is what keeps the climate of the surface world as stable as it has been throughout human civilization. The Gulf Stream, which most people have heard of, is part of this system. Warm water flowing northeast across the Atlantic toward Europe is one surface branch of the conveyor, driven forward by the need to replace water that descended through those underwater waterfalls in the north. Western Europe sits at the same latitude as large parts of Canada, Labrador, Newfoundland, but has dramatically milder winters. The conveyor is a major reason why. Without the waterfalls filling the deep, the conveyor changes. That isn't a future tense statement. It's something the planet has already demonstrated, more than once. Around 12,900 years ago, the North Atlantic circulation slowed substantially in a matter of decades. The likely trigger was an enormous pulse of meltwater from glacial Lake Agassiz, a vast body of water that had accumulated behind ice dams as the last ice age wound down across what is now central Canada. When those dams gave way, an enormous volume of fresh water drained into the North Atlantic in a geologically short window of time. Fresh water is lighter than salt water. That flood of meltwater diluted the North Atlantic surface enough that the sinking mechanism failed. The water was no longer dense enough to descend through the Denmark Strait at its normal rate, no matter how cold it got. The conveyor slowed. The heat stopped moving north with the same intensity. The result, within decades, was a significant temperature drop across the North Atlantic region. Europe and Greenland returned to near glacial conditions for around 1,200 years, cold enough that a cold-adapted Arctic flower, Dryas octopetala, spread back into latitudes where it hadn't grown since the full ice age. Scientists named the period after it, the Younger Dryas. Then, roughly 11,700 years ago, the circulation restarted. Temperatures rebounded sharply, possibly within a decade or two by some ice core estimates. The cold period ended almost as abruptly as it had begun. Human populations at the time were small and scattered, but the climate shift within individual lifetimes was profound enough to reshape which species lived where and which ecosystems could support which communities. The lesson from the Younger Dryas isn't that the conveyor is fragile. It's that it can shift meaningfully when the freshwater balance in the North Atlantic changes enough to affect sinking rates. The reason that history is relevant today is that fresh water is entering the North Atlantic again, from the melting of the Greenland ice sheet. The mechanism is the same one: lighter fresh water diluting the surface, reducing the density contrast that drives sinking at the Denmark Strait and related overflow sites. Measurements of the Atlantic circulation show that it is currently running more slowly than at any point in the last several centuries, possibly longer. A monitoring array called RAPID, a line of instruments stretched across the Atlantic at around 26 degrees north, has been continuously tracking the circulation since 2004 and shows that it has weakened over that period. Whether this trend will continue, plateau, or reverse depends on factors that climate scientists are actively researching. The measurements are real. The future trajectory involves genuine uncertainty. What a meaningfully slower conveyor would look like in practice isn't a sudden catastrophe. The scale of any realistic near-term change is far below what produced the Younger Dryas, and the speed of that event was associated with a meltwater pulse far larger than anything currently projected. What scientists are more concerned about is a gradual shift. Less heat delivered to the North Atlantic, altered rainfall patterns in West Africa and South America that depend on the position of the tropical rain band, changes in the frequency and track of Atlantic storms. Colder winters in the UK and Northern Europe is one possibility that gets discussed, though the magnitude and pace of any such change is uncertain and debated among researchers. The overall global warming signal is strong enough that some of these regional effects might be masked or offset by direct warming. The science here is live and actively contested in the peer-reviewed literature, not because researchers doubt the measurements, but because the system is complex enough that predicting specific regional outcomes is genuinely hard. What isn't contested is the direction. More freshwater input to the North Atlantic reduces sinking rates. Reduced sinking rates slow the conveyor. A slower conveyor changes how heat is distributed across the Atlantic basin. The physics is clear. The magnitude and timing are where the uncertainty lives. Carbon is the other side of this that rarely gets enough attention. Surface ocean water absorbs carbon dioxide from the atmosphere constantly. It's a basic chemistry interaction between seawater and air. When that surface water becomes dense and sinks through the thermohaline circulation, it carries its dissolved carbon load with it, down to the deep ocean, where it stays effectively out of the active carbon cycle for as long as the deep circulation holds it there, centuries in most cases. The ocean currently absorbs roughly a quarter of all the carbon dioxide humanity emits each year. Part of that absorption ends up in the deep ocean via the sinking currents, the same sinking that feeds the underwater waterfalls. Slow that sinking, and the fraction of emissions that remains in the atmosphere rises. Not dramatically, and not immediately, but the relationship is real and measurable. This is why oceanographers have been paying increasingly close attention to the RAPID data and to related measurements of deep water formation rates at various sites around the North Atlantic and Southern Ocean. The waterfalls are not just a feature of interesting deep-sea geography. They're part of the machinery the planet uses to manage its own carbon balance, and changes to their intensity have consequences that spread upward through the entire ocean system. There's a concept that oceanographers use called abyssal memory, and it's one of the more quietly striking ideas in the field. Because the deep ocean moves so slowly, the water down there remembers where it came from. Water sitting in the deep North Pacific right now carries the chemical fingerprint of the polar surface conditions that existed when it was last at the surface, possibly centuries ago. The temperature signature, the salinity, the concentration of dissolved gases from the atmosphere at that time. All of that information is preserved in the water, slowly drifting along the ocean floor, as a record of what surface conditions were like when that water sank. Scientists access this memory by analyzing water samples taken at various depths during research cruises. By tracing the chemical signatures of different water masses, they can identify where and roughly when various parcels of deep water were last at the surface, building a three-dimensional picture of the ocean's circulation history over decades and centuries. Sediment cores go further. The material that settles onto the deep ocean floor, tiny shells, mineral particles, organic fragments, records the conditions of the overlying water column at the time of deposition. Drilling into the sediment and analyzing what's there, layer by layer, is reading the ocean's diary going back millions of years. The younger Dryas shows up in those records clearly, a distinct chemical signature marking the period of reduced circulation, followed by the sharp shift when the conveyor restarted. Every major reorganization of the deep circulation has left its mark in the sediment. Opening of the Drake Passage between South America and Antarctica, which transformed the Southern Ocean from a sluggish basin into the cold, productive engine of the modern circulation. The gradual cooling of global deep waters over the last 30 million years as Antarctica glaciated and began producing cold bottom water at scale. The repeated glacial-interglacial cycles, each one involving substantial shifts in where and how fast water sank, all recorded in the chemistry of the deep sea floor. The waterfall isn't just shaping the ocean right now. Its history is written into the sediment of every ocean basin on Earth. Something worth sitting with as this video gets toward its end. The deep ocean does more hidden work than most people ever consider. Half the oxygen in every breath you take was produced not by forests, but by phytoplankton in the surface ocean. Microscopic photosynthetic organisms that are invisible individually, but collectively outnumber every other photosynthetic life form on Earth. When those organisms die, the carbon they built themselves from sinks, as marine snow, slowly drifting toward the ocean floor. Some of it gets decomposed on the way down. Some reaches depth, and that portion is removed from the active carbon cycle for centuries. The underwater waterfall is part of the pathway that carbon takes. Dense, carbon-carrying surface water sinks through the same mechanism, driven by the same density differences, delivering its chemical load to the deep alongside the organic carbon drifting down from above. The deep ocean is both the destination of carbon sinking from the surface and the reservoir that holds it there, and the circulation powered by the underwater waterfalls is what keeps that reservoir turning over on geological timescales. Scale that up and the number is significant. A quarter of all human CO2 emissions, absorbed by the ocean every year, partially transported to depth via these sinking currents. The waterfalls are part of a natural carbon management system that predates human industry by hundreds of millions of years, and that human industrial emissions are now interacting with in ways that are still being quantified. The next time you look at the ocean, from a shore, from a ferry, from a photograph, the surface is only the top few percent of what's there. Waves, sunlight, wind chop, whatever the weather is doing, all of that is happening in the shallows, really, regardless of how deep the water gets beneath it. Below that visible layer, in the dark, the real machinery is running. Dense water formed at the Greenland Sea last winter is making its descent right now through the Denmark Strait. Antarctic bottom water is spreading across the floor of the Pacific, carrying chemical memories of the Antarctic winter from a century ago. Mediterranean water is flowing westward through the Atlantic at intermediate depth, 3 months out from Gibraltar, still holding its distinct salinity signature. None of this is visible from the surface. Satellites can't image it. Passing ships don't feel it. For most of human history, nobody knew it was happening. What we now know is that the largest waterfall on Earth is down there, driving a circulation system that distributes heat around the planet, pulls carbon into long-term storage, delivers oxygen to the deep sea floor, and has been doing all of this simultaneously for longer than our species has existed. Knowing it's there doesn't make it visible, but it does make the ocean feel different. Not smaller, but considerably larger, and considerably more active than anything you can see from the surface would suggest.